behavior as non-deterministic systems. And that allows you to evaluate and test systems that couldn't be validated using conventional assurance methods. Autonomy frameworks are typically differentiated by their policy and how they choose among multiple simultaneous controllers. Some fail over to a secondary controller, and some prioritize an experimental controller that might be more optimal, and then fall back to a suboptimal proven controller if it has to. And some autonomy frameworks use one controller to fly the vehicle and drive the perception in an experimental controller, which is never given control over the vehicle. EVA is NASA's contribution in this space. It runs multiple controllers in parallel. All the controllers are independent, which helps manage compounding complexity. And if any controller issues an unsafe control action, then that action can be superseded by one of these supervising controllers that act like guardrails on the system. Any outer loop command control action can be preempted even before hitting its command target, which yields more complex and emergent behaviors. EVA was designed to be vehicle agnostic and autopilot agnostic. And it's the result of about 4 decades of work at NASA Armstrong on automated maneuvers on the F-16. Critical to the acceptance of these earlier systems was ensuring it didn't impede the pilot in any way, which meant that these systems often operated on timescales less than pilot reaction times. And it's important to note that the F-16's ground collision avoidance system is not considered safety critical. It's considered a mitigation. It also assumes full control authority, so if there was a loss of control and the automatic maneuver failed to recover the system, would the outcome be any worse than if the system wasn't there? It wouldn't. It makes a last-ditch effort to recover the aircraft, and so far the ground collision avoidance system based on these concepts has saved over a dozen lives. The trifecta of design goals that kind of flowed into EVA as a result of all this work is shown on the patch there in the corner. And these design goals were baked into this runtime assurance concept. Do whatever you want, except harm. So from an assurance point of view, you can't specify everything that a system will do in all circumstances, and maybe it's sufficient to specify what it won't do in any circumstance. Essentially inverts the design paradigm. And for autonomous systems, it seems like you need both. So the runtime assurance design process is to identify your potential losses, identify the unsafe control actions that lead to those losses, and then identify the performance and sensory requirements that help you detect those unsafe control actions, and then you knowledge engineer an automatic recovery to supersede an unsafe control action. This is from the ASTM standard on runtime assurance. It's an illustration of the ground collision avoidance system used on the F-16. You've got the safety monitor that detects the unsafe control action, the recovery controller that rolls the wings level and does a steep climb, and then a decision module that switches between one of the two controllers here. By 2018, NASA extended this concept to multiple monitors and multiple recoveries. They call this the multi-monitor runtime assurance. And by last year, they extended it to multiple decision modules. So all the previous work was focused on external hazards and used tactical recoveries. The extension incorporates internal hazards that are triggered by a data integrity system called SWIM. So if you had discording sensor observations or you detect a loss in control authority, you can trigger a contingency behavior like return to base or forced landing. It's been fielded on these manned and unmanned systems and also has been used to drive instrumentation for like a pilot awareness display. The trend is larger and faster aircraft and also more complex environments. Just a couple months ago, we fielded EVA as a surrogate for a low-cost thermal sensor for a detect and avoid application, and we were able to detect and track unresolved red team targets from a flying platform at a range of about 800 kilometers. Dr. Snarsky from MTSI has a paper in SPIE on that if you're interested. EVA is like an operating system. All it does is provide an environment for other processes to run, and the meat and potatoes would be your hazard monitors that implement some sort of threat assessment and produce some sort of recommended action, along with a knowledge engineered consequence. The decision module, all the commands, it can make a decision as to which is the best, and then it forwards the selected command to an autopilot coupler that just translates the internal command into something your autopilot can understand. So all the communication inside EVA is mediated by this centralized database, which is essentially Carnegie Mellon's Blackboard agent architecture. And in pertinent part, we have a telemetry stream, a data distribution service here, and an onboard mapping system, which supports multiple layers, roster, vectors. So you could load your sensor data there and then use its API to do your threat assessment to simplify things. There's also other components, but one I'll mention here is a component called Crosstalk, which is kind of it implements a stigmergic approach to communication between monitors. They're independent, but they can exchange information kind of like on their own Blackboard. They can mark non-viable maneuvers on a model of the environment. and other monitors can choose to look at that and kind of abort maneuvers that it wouldn't consider anyway. So that contextualizes our work on NASA's autonomy framework. Any US company can license that from NASA, but it's not well documented. And so our research questions are listed here. NASA's made plugins for ground collision avoidance, air collision avoidance, geofence, waypoint following, terrain following, well clear, obstacle avoidance, a number of things. And MTSI has made a number of plugins for environmental hazards, as well as other things for SOCOM. But the focus has been on safety, but the big picture for these autonomy frameworks is to enable non-deterministic and AI-enabled systems. So we expect there to be a growing number of enablers, AI-enabled planning and perception algorithms. And we also expect the number of plugins to increase with the complexity of the environment. So the first question is, how many plugins can we add to EVA before breaking something? The second question had to do with deploying this on faster aircraft. The reflex is to just throw faster hardware at it, but we wanted to verify. Then for applications where you have robust communications, we considered using EVA for tracking a missile on a test range, using a geofence to trigger a flight termination system. But what kind of resolution can we get on that asset? And swarming applications might also require vehicle-to-vehicle communication, so what are the telemetry stream limits in terms of data volume and rate? And finally, NASA's got a set of prediction plugins on the shelf that can be tuned to arbitrary fixed-wing aircraft, but using those involves some sort of tuning process that they haven't documented, and all we know is it takes them 1 to 2 months to perform, and the guy who knows how to do that just retired. So our focus was trying to figure out how to use these plugins rather than recreate the wheel. So regarding the first question, we took a model-based approach. The model takes into account pertinent system parameters, and the objective function tried to balance the trade-offs between utilization and configurability, and found that the Goldilocks zone, according to the model, is 4 processes per core. And that aligns actually more with NASA's more recent empirical finding of the same. The framework supports up to 8 cores. So according to the model, you can run up to 32 processors, but there's a core affinity mask in the API that you can probably change to Win64 and support like an AMD EPIC and get up to 256 processors. But we've got another solution that we'll mention a little later. Regarding hardware selection, we ran a ground collision avoidance workload on different platforms, and we captured runtimes. We traced the runtimes down to the underlying hardware and traced the runtimes upstream to the code component, software component that contributed to the runtime. So the findings are in the paper, but the one I want to point out is the effect of clock speed on runtime. You can see it bottoms out at about 700 megahertz, which indicates algorithmic limits on performance, and by extension, limits on component reuse. So you might need vehicle class specific plugins. So regarding the upstream contribution to this particular workload, the ground collision avoidance hazard monitor essentially delegates the whole threat assessment to the map manager, which takes up a third of the entire runtime. The map manager is the sensor for the ground collision avoidance system. This flowchart illustrates the streaming process. Basically packing and sending messages out to all the connected clients takes time, so we were interested in capability limits. Again, we took a model-based approach, took into account the pertinent system parameters, and these were our findings. And finally, kind of the 800-pound part of this 6-month effort was evaluating NASA's trajectory predictions. So there's 2 plugins we evaluated, a 15-parameter fixed air. These figures show the effect of perturbing each parameter in the general aviation prediction by 1 order of magnitude, just to illustrate the process capability as well as process mean. But for us, we didn't even know what the range for each parameter was, so we started by testing the neighborhood of the NASA configured value and then just moved out until we broke the system. And then within those tighter limits, we did a high resolution scan doing about 2 million simulated flight tests to capture both the range of the parameter and the response metrics. There's 2 response metrics we use, the total distance traveled and total heading change for 2 different maneuvers. And you can use this data to now inform a fractional factorial study. We mainly focused on first order effects, and we captured second order effects for some of the Boolean parameters. We also produced tables like this, which allocate parameters along 2 different axes, maneuver as well as response. And we normalized the parameter range to a percentage, and then for each 1% change in input, computed an average response. And the reason we did this is so we can create a ranked order of parameters so that you can pick a subset of these parameters and their coefficients whose sum yields your target distance traveled or target heading change. Because those tables average the response, you have to look at a number of plots like this to see what the actual response is. So essentially, our contribution as far as the trajectory predictions are concerned is we characterize the parameter ranges, parameter effects, and we essentially propose the Six Sigma design of experiments workflow. We were running out of time, but we did try to use one operations research algorithm called Simplex, which essentially required taking our plots, making a system of piecewise linear equations, inequalities, each of which defines a hyperplane in either 15 or 71 dimensional space, and then the whole set of inequalities defines some sort of region in that state space. The algorithm basically just tests the corner points on that region. And in hindsight, I mean, perfectly obvious now, but it tended to maximize a couple of the parameters, so it didn't produce useful results. So going forward, we're going to continue exploring auto-tuning algorithms to help simplify this tuning process so the community can reuse NASA's plugins. And we're also implementing a microservice architecture to address process contention, and that's for vehicles where the issue isn't raw compute power, the issue is utilization. It's the same thing that happened with like data centers. You had bare metal systems, fixed resource, fixed capacity, but underutilized. And then for larger systems, like virtualized environments, the issue becomes utilization. We're also swapping out the CVT stream, the telemetry system, with a open source pub sub data distribution service. So that's all for me. Thanks for attending. Are there any questions? Yes, sir.
Go ahead, sir.
Your architecture, I think you said that if there was a contingency that comes up, could trigger a response behavior. But what if the response behavior requires the other safety monitors as well? So if my drone runs out of battery on the other side of Newark Airport, I don't want it returning to base across Newark Airport. I want it to still stay safe returning to base or landing. How do you manage safety if you're executing a contingency behavior that was triggered by some other safety?
So if you were doing one of those kind of longer contingency behaviors like return to base, it doesn't deactivate any of the more tactical behaviors. So on the way back home, if you had to go through a mountain, it would still avoid that and get around that. So good question.
Anything else? Okay, thank you,
Thanks,
Raul.
Bruce.